Hello guys, today we're going to talk about 6.1 rational functions and multiplying and dividing rational expressions. First thing we're going to do is we're going to talk about domain and range and some asymptotes that occur when we have rational expressions and we're trying to graph them. So what I'm going to ask you to do first is to take number one and put it into your graphing calculator, or you can go ahead and put it into Desmos. And I want you to take a look at the graph. So go ahead and pause the video and do that right now. So this is probably what your graph looks like right here. You might want to zoom out so you can see the full graph, but you'll see that there are two parts to it. You'll see this one up top and then this one out for the bottom. Now these aren't just regular parabolas as we might have thought with the squared, but a couple things I want you to notice. Do you notice if we were to zoom in kind of hard further in right here, that what happens is there is this asymptote that occurs right here, and you'll notice that it's getting closer and closer to -6. And what we talked about before is that with asymptotes, the graph approaches the line but will never touch. So that keeps going on forever. But it also, if we zoom back out and go back down this way, you'll notice the same thing over here. It's going to approach that -6 but never touch. Another thing I want you to notice that this right here appears to be a line. It's a slant asymptote, but we'll get to that later. For right now, I want you to focus on this right here. Now let's go back and look at those equations, or this equation. So if you take a look, we have x squared plus 1 over x minus 6. Sorry, that should be x plus 6. And then let's look back at the graph, and you'll see that the asymptote is at -6. Well, that's because if you think about what's happening here, if I set this equal to 0, x equals -6, we know that x equals a number is a vertical line. And if we also think about this, if we have 0 in the denominator, we know that it does not exist. There's not a number that exists, so it's undefined. So it should make sense that when we look at the graph, that there is a vertical asymptote, meaning the number does not exist at -6, because you cannot have 6 in the denominator. Now let's think about number 2. And if we go ahead and look at the graph for number 2, you'll see a few things happening. You'll see an asymptote here and here. You'll notice that it's at x equals 5 and x equals -2. So why might that happen? Well, if we take a look at the denominator right here, and if we factor it, x minus 5, x plus 2, and then we set it equal to 0, x equals 5, and x equals -2. These are, again, where those asymptotes are. Therefore, the function cannot exist right there. So what do you think about 3 and 4 then? If we were to try to graph those, where do you think the asymptotes would be? Hopefully you said the asymptote would occur at 3/5 here, or x equals 3/5, and the asymptotes would occur at x equals 3 and -3. Now, since they don't exist at that point, when we talk about finding the domain, we would say that the domain is all real numbers except for x cannot equal 3/5 and x cannot equal 3 or -3. We could write this a number of different ways. One way when we talk about interval notation is -infinity to 3/5 union 3/5 to infinity. But what we can do right here is we can just say, do the subset x such that x is a real number and x cannot equal 3/5. And then the same thing would be true with number 4.